All right. So the last time I was talking about that so this is what we breathe, the O2 molecule. The ozone is made of O3 molecule, right? So that's found in the upper atmosphere, roughly 25 kilometers above the surface of the Earth, in the region called the stratosphere, uh, as I mentioned before. But what's important about that is it protects life, like you and me and other forms of life on this planet, from ultraviolet radiation. That ozone layer protects us. Um, However, there's been times when um, humans have used. Let's see, do they talk about it? These what are they called? CFCs, chlorofluorocarbons, and those break up the O3 molecules, and there's even been holes in the ozone layer. But that particular type of molecule, that CFC, has been banned by most countries. Hopefully, in the future, it'll be banned by all countries. But it used to be like, back in the 1970s, it was in hairspray, for example. People use that. That's just one example of it. All right. So now, where did the Earth's atmosphere come from? Where did the oceans come from? All right. So one of the theories that was put forward, I think it was starting in the 1960s or so, is naturally when volcanoes erupt, there's a certain amount of water vapor that comes out. There's carbon dioxide. There's nitrogen that comes out. But also, we realized that if you look at the volcanoes around the Earth, and then you do a statistical analysis and say, okay, how much volcanic activity has been going on for the past 4.5 billion years, you don't get the amount of water and carbon dioxide and nitrogen from volcanic activity on the Earth. And so some other people, like I said, it's starting around maybe the 1950s, 60s, um, started proposing the idea that maybe asteroids hitting the Earth, or even comets. Comets are basically gigantic, dirty snowballs, and so there's lots and lots of water in comets. And in the early part of the solar system, this is one of the things we're going to talk about a little bit later, is that there was this what's called the late heavy bombardment, where the Earth and the other planets were bombarded by lots and lots of asteroids and comets. Now this was billions of years ago, about almost 4 billion years ago, um, and so that the amount of water and carbon dioxide and nitrogen built up over time. And now you might say, well, where did the oxygen come from? And so the oxygen actually comes from plants, right? The O2 molecules come from plants, from photosynthesis. So then the plants need, of course, water, and they need carbon dioxide, and they need sunlight as well to photosynthesize. In the very early atmosphere, we think that it was mostly made. The atmosphere was made of methane and ammonia, but that was broken down by the ultraviolet light into other molecules, like nitrogen N2, and most of the free hydrogen escaped into space because it could easily reach the value of the escape velocity of the Earth, and free hydrogen atoms would just take off from the Earth. Again, plant life happens on the Earth, billions of years ago, and that over the process, over this the process of photosynthesis over the period of geological time, that has created about 21, almost 21% of the atmosphere is now the O2 molecule, the stuff that we can breathe. Of course, with the air and the oceans, there's circulation that takes place. For example, the Gulf Stream, the hot waters of the tropics follow the Gulf Stream up towards up towards England. England would be a much colder place, in fact, if it wasn't for the Gulf Stream waters. But that's just one example of the Gulf Stream. There's lots of these currents, right? These are currents that travel from hot to cold, and one of the things that drives this in the atmosphere and in the ocean is what's called the Coriolis effect. The Coriolis effect is basically this idea that because the Earth is it's a real thing. Because the Earth is rotating, if you were to let's see let's see. All right, so I mean, this is actually well known. This Coriolis effect. For example, if you were to fire a missile, well, straight down, from the North Pole to the equator, the Coriolis effect would cause the missile to be deflected, right? It's not an actual force or anything. It's just the fact that the Earth is rotating, right? So that's this phenomenon called the Coriolis effect, and we see this the Coriolis effect, for example, in the northern hemisphere is what causes when you see the hurricanes, right, on the East Coast, for example. I mean, you're probably very, very familiar with hurricanes in the East Coast. They're always rotating, counterclockwise, and that's because of the Coriolis effect. Right? And of course, the jet streams are caused. That's just because of the sunlight heats up the upper atmosphere, and then as the Earth rotates out of the sunlight, it cools off, and hot seeks cold, and so there's these jet streams in the upper atmospheres. We actually see this kind of thing going on other planets. Here's an example, of course, of Jupiter, the biggest planet of them all. But we see these bands. These are called zones and bands. We'll get to that later. But the great red spot on Jupiter is actually a giant storm that is circulating around. We see this kind of thing also on Saturn and in Neptune. We see this Coriolis effect take place. All right. One other thing about the Earth. The Earth is actually slowing down. The Earth is actually slowing down over a real long period of time. And so what happens is the Earth, just like if you had a top and you were spinning a top, the top, as you watched it spin, as it slows down, it kind of wobbles, right? And that wobble is what we call precession. And, humans have known about precession for a while now. And so what happens, so here's an example. So the top slows down and it begins to wobble. And that's exactly what happens to the Earth. Now, it takes 26,000 years for the Earth to wobble around once. It's not like it's not a huge deal for us. Within a human lifetime, it doesn't hardly move at all, right? So right now, the North Pole is pointed really close to the star Polaris. Over time, 8,000 years from now, it'll be the North Pole will point kind of in the direction of what is that? That's this is not a super bright star. This is just part of the constellation Cepheus called Aldebaran. I mean, it's somewhat bright. It's maybe a little dimmer than Polaris. But then, as time goes on, if 14,000 years from now, the North Pole will be in the same direction as Vega. Now, Vega is a really bright star, right? Which, by the way, that means that 14,000 years ago. Sorry, sorry about that. Yeah, 14. 14,000 years ago, Vega was near the North Star, right? 4,000 years ago, there was this another star over here, a relatively bright star called in the constellation Draco called Thuban. I mean, these stars are still there. It's just where the North Star points, or where the north points varies with time over you're talking about thousands and thousands of years. All right. So, all right. So we got the greenhouse effect. I mentioned that before. All right. So the water cycle. I think that is pretty much our chapter. All right. Let me pause this. All right, let's do one example. So I'm going to use the Earth as my example here of calculating density. Okay, so remember, density is mass divided by volume, m divided by v. So the volume of any spherical thing is 4 times pi divided by 3 times the radius to the third power. Now m has to be in. So the normal thing that we do is m is in grams, and the volume has to be in centimeters cubed, or cubic centimeters. All right, so we have two conversions here. One conversion, 1 kilometer is 10 to the 5th centimeters, and 1 kilogram is 1,000 grams. All right, so now if I put the mass of the Earth and the radius of the Earth, I can calculate this. All right, so let me pause it, and then I'll do the calculation. So here's the quick conversion. So what I'm doing is, where's my mouse? There it is. So 6 times 10 to the 24th. There's 1 kilogram in 1,000 grams. So you multiply that, you get 6 times 10 to the 24th times 10 to the 3rd. You just add the exponents. All right. So that's 20 to the 27th grams. So the mass is that. And then R is because there's 10 to the 5th centimeters in a kilometer. The kilometers cancel, right? And so this becomes 6,400 times 10 to the 5th. All right. So we're going to plug that into this formula, and let me pause it because I'm running out of time. All right. So with this one, so there's the mass. 6 times 10 to the. This is supposed to be 27th. grams. All right, 6 times 10 to the 27th, because that's what it turns out to be. And then you take 4 pi divided by 3, and then 6,400 times 10 to the 5th, but then you cube that, you get approximately 1.09 times 10, 1.098 times 10 to the 27th. All right, so you take, remember, it's the mass divided by the volume. So you take the 6 times 10 to the 27th divided by 1.09 times 10, 1.098 times 10 to the 27th, and you get about 5.46 grams per cubic centimeter, which rounds, if you round it to one place past the decimal, it becomes 5.5 grams per centimeter cubed, which is, of course, the density of the Earth, right? That's how you get the density of the Earth. Okay, so try this calculation. That's a good example of how to get the density of the planet Earth. All right. Remember, you can always come to my office hours if you having trouble putting this stuff into your calculator. Remember, you got to use, when you put times 10, you don't ever hit times, you don't ever hit 10. All right. So my
I say that in class all the time to make sure that you are aware of that.